have enough time, so we can dedicate about 20 minutes to each of the papers. I will try to keep rigor, but anyway, I think there will be time for questions, and I hope we will have a lively and useful discussion. Welcome again, and let me introduce the first paper. So, our first paper today is Hardening the Loop Test Bed for Load Management Applications, and authors are Seper Nakostin, Mr. Rodriguez, and Mr. Belometti and Mr. Omati from ABB, and presenter is Seper Nakostin. Mr. Nakostin received his master's degree in electrical engineering at Politecnico of Milan, and he dedicated his master thesis to real-time simulation applications. Please.
Good evening, ladies and gentlemen. First of all, I'm delighted to express my interest on behalf of all team members for the opportunity to talk about our work among other scientists, researchers, and engineers. My name is Seper Nakostin, and I will be your host for the next 20 minutes. The aim of our project was to design an agile tested system for load management applications. The project has done through intense cooperation between Politecnico di Milano University and ABB, the Bergamo branch. Energy consumption in general and electricity in specific plays a significant role in nowadays daily people's life, from very basic needs like warming up the meal to very sophisticated ones like economical progress and social development. If you have a look at the first graph, which has been released by the World Energy Outlook in 2016, you may find a direct relation between GDP growth and the energy consumption. So the higher the GDP growth is, the more energy consumption will. However, unfortunately, still noticeable amount of energy generation is through carbon-based technologies. Needless to mention its environmental impacts, from deforestation to carbon monoxide emission, global warming, and so on. Here is the point which engineers come, and they would like to find a solution to meet people's needs, to meet their needs, like their ambitious goals for economical ambitious goals, and meanwhile oppose the environmental impacts. If you have a look at the second graph, which again is released by World Energy Outlook in 2016, which in my opinion is an interesting one, you will find the projected GDP growth in the world compared with the electricity generation. If you have a look, the electricity generation won't follow the same pace as the GDP growth does. So why it's like this? Will the electricity lose its role? Of course not. The answer relies in improving the efficiency, and efficiency is the motor of the change and key of the change. Smart load management systems, or in other words, automated systems for power management, have recently received an increased attention. They are not only capable of optimizing efficiency, but also capable of extending the current energy source's lifetime and their relevant infrastructures. They also make the smart grids possible. Here is the solution which ABB provides for smart management application. There's electronic embedded units in the main breaker of the installation, which, when I'm talking about the embedded unit, it means no extra devices is required, no extra wiring also is required. This electronic unit is responsible for, by help of this electronic unit, we are capable of performing complicated load management scenarios, from totally distributed ones to completely centralized ones, also with different scenarios. with different purposes. In coming slides, I will briefly talk about this electronic unit. Here in this image, you can have a better look to this electronic unit, which from now on, I prefer to call it controller. This controller receives 6 signals, 3 for voltages, 3 for currents. This controller is responsible for calculating the downstream load power consumption and taking the proper actions. It also provides some auxiliary inputs. The controller works based on the average foreseen power consumption, which this will avoid of unnecessary switching due to temporary high power consumption. If you have a look at the graph, you will see that the plane has been divided to 3 zones: the acceptable ones, high consumption zone, and reduced ones, by help of the polynomial curves. And the polynomial curves themselves, they have been calculated based on number of loads, the nominal power, and the limits which you want, the threshold which you want to limit the power consumption. If you have a look to the power trend, you will see that from one point we exceed the acceptable zone, and it continues in the high consumption zone, because we are still within the average power consumption is still within the acceptable range. If I'd like to point out some other tools which are provided by the controller, I should name the selective feature, which not all the it's not mandatory to include all the loads in the power controller cycles. Like elevator, you can exclude some load from the cycle. Priorities, you can assign the priorities due to the importance of the load. So to disconnect some loads as late as possible and as least as possible. Like industrial refrigerator, which the foods can be exploited. The controller can respect some special times. Some loads are required to be connected to the power for at least minimum times, like the battery chargers. Some of them cannot be disconnected from the power more than a specified time, again like the industrial refrigerators. Also in rush current peaks and voltage perturbations are avoided due to the fact that we are not connecting and disconnecting the load simultaneously. Also for the loads with the same priority, the controller will connect and disconnect the loads with the fewer number of switching in the history, so to postpone the aging. Also remote controlling, we are capable of, we are not limited to the vicinity area of the controller, and we are able to communicate through the Ethernet network and monitor a wide area. Okay, here the described features are depicted in a simple example as like a textile factory, which you will see that there are a couple of loads with different priorities from left to right. The priorities are decreasing, so the one on the right can disconnect more frequent than the others. None of the loads have been connected or disconnected together simultaneously, and the total final average power is within the acceptable range. If I like to end up the rest of the features of the controller, I have to point out that this controller monitors the total power consumption. So there is no need to monitoring individual loads. Since the controller is only interacting with its downstream loads, the information overflow is prevented. So we are not communicating with all parts of power plants. Although the controller may interact with a large number of loads, still it can behave as a single entity and can communicate with higher level controller. Okay, so far we've talked about a product which has been developed by ABB, but what we have done beside this product, we have developed a platform to show and to demonstrate these features to the clients, to train them for troubleshooting, for commissioning. Even we provide the platform for debugging and validating the firmware for the manufacturer itself, with possibility of different complicated scenarios from simple to complicated ones. And the last but not the least, we've also checked out the final effect of the controller on some other subsystems controller, which I will discuss this feature in coming slides. Okay, the HIL architecture simply begins with collecting every load status, calculate the corresponding power, convert the calculated power to corresponding voltage and current, and finally receives a closed loop in real-time measurements to the controller, and so controller is able to perform, to take the desired actions. If you remember, I said that the controller requires 6 signals. However, here in this slide, I would like to talk about a strong feature that we've applied on our platform. The solution that we've offered works only with 2 analog outputs. So by help of only 2 analog outputs, we are required for smaller modules, so cheaper ones. So this is one of the things that the tips that we've taken into account to make our solution cost effective. Here you can see also some functions and coefficients which have applied into our software based on exactly real condition. For example, for the current which has passed, which are past the currents which are passing through the Rogowski coil, we have applied the derivation because the measured signals has the intrinsic of the voltage, and the other issues with the sampling frequency of 1 kilohertz, 5 cycles of sampling, 100 samples per each cycle. And as I said, there are only 2 analog outputs were required. User interface was always a big concern for us. Since this part is the point which the users have to deal with the complicated logics, it has to be as simple as possible, completely straightforward, user-friendly, and without any extra components. If you also have a look to these features, to these tools, the user can change the nominal absorbed power from 0 to its nominal 1. Also, the power factor can be set from 0 to 1. Also, the behavior of the load from inductive to capacitive, from load to generators are adjustable. Also, the graphical status of the loads are presented with the trip mode indication, and the corresponding input voltage and currents to provide some idea to the clients that how much is the displacement factor, power factor, and how the total absorbed power looks like. As I just said, one of very important concerns of our work was to prove that the controller won't affect negatively any other controller. So imagine this room that we are having an HVAC load, and this load is supposed to set the temperature of the room within a preset values. And if I'd like to monitor the cooling system, it shouldn't affect the final results, which is the temperature of the room negatively. So we have developed the thermal model with total energy stored in the room plus the energy exchanged through walls and windows, and plus the hot air leaked out of the room per hour due to opening the windows or doors or something else, which has to be equal to the total energy consumed by the heater, and taking into account that the temperature has charging and discharging likewise trend. So we have placed our cooling system, our heater, under the power controller, and we saw that the results, which it shows that the controller didn't affect the final operation negatively. Here is also another real study case on HVAC loads in Northern Europe, which half of them were only under the surveillances of the controller. 4 megawatts totally was the total load, which half of them, as I said, were under the supervision. If I'd like to have some conclusion, I can provide some conclusion from training point of view and also economical ones. We have provided a flexible, closed-loop, real-time system with completely, absolutely simple interface. The logics, although the computations were vast and large, the implemented logics were completely fast and reliable. And on the portable module that we have created, and I guess right now it's on the market, the actual switches were on its portable module, so the clients can see the switches on and off, getting on and off, switching on and off by help of the power controller. From a economical point of view, as I just said, it was cost effective, not only because of reducing the number of analog outputs, but also due to the fact that the software is standalone, so the final client is not supposed to purchase any software or something. All the hardware and softwares are selected out of off-the-shelf products. So we didn't use any special things. We didn't pay any extraordinary prices. The time required for setting up and commissioning have been reduced enormously, and also it's on our solution adding some other loads in future was also possible. So this could be also classified, the last one, as training tool facts. Okay, what we've done, actually we have verified the pros of automated systems through developing the HIL testbed system by developing 4 load small scenarios, by developing a thermal model to verify the functionality of the controller, and also we have performed a real study case over the HVAC load management in northern of Europe. We highly believe that this HIL testbed system will find a way, we'll find a wide application on test, training and demonstration, and will give a significant contribution to automated systems for power management to extend their application as a world-class player in future. Thank you very much.
Thank you very much. If there are any questions from the audience, it's time to ask them. If there are no questions, may I ask one?
Sure.
What was the most challenging aspect during the development of your simulation system?
The most challenging ones, since it was we were supposed to implement the system, I can remember that every part had its own challenge, because we were supposed to purchase some products, implement them, figure out. One part which, of course, it was not mentioned in this presentation was to actually running a drive, and that for 11 load management application, which was a complicated one. That part was among the most challenging parts. But here, maybe the thermal ones could be the most challenging one. since we had to develop the model out of experimental issues. So we've ran the model under the test for many hours to figure out the best equations ever possible.
Okay. Thanks again.
You're welcome.